Almost all of today's counterflow cooling towers have the same three problems that significantly downgrade their performance. Uneven water loading as a result of overlapping circular nozzles. Excessive wall water as a result of using circular nozzles, and inadequate water distribution systems. Almost all cooling tower nozzles spray in a round or circular pattern, and that's a problem. A circle won't cover a square unless it's really oversized. So to compensate, companies design in an overlap in the spray pattern to eliminate these voids. So why does this matter? First, let me tell you how film media works. Cellular film media consists of a series of corrugated flutes bound together to form a log. Each of these flutes, in essence, becomes a small cooling vessel specifically designed to accommodate 25% of the flute opening being allocated to water loading, and the remaining 75% flute opening dedicated to airflow. Any deviation in this 1:3 ratio of air to water mixture will significantly degrade the performance of the cellular film media. So here is what happens when you overlap or flood the film media. As you can see in the graphic, the water loading becomes heavy where the overlap occurs. This overlap creates a high-pressure drop, restricting airflow in these areas. The blue arrows depict the restriction to the airflow, resulting from the high-pressure drop, and the heavy water loading of the overlap. The restrictions caused by the overlap cause the remaining air volume to be forced into areas where the water loading is light. Both the volume of air and the velocity will increase in these areas. The red arrows depict the accelerating airflow exiting the film media at high velocities, a gross waste of fan energy. The same circular water pattern of the spray nozzles hits the walls on the perimeter of the cooling tower, flooding the film media in these areas. So what's so bad about wall water? It had to be pumped to the top of the cooling tower. It flows down through the flooded areas of the film media, mixing with little to no airflow, and as a result, receiving poor heat transfer. As with the nozzle overlaps, the airflow in this area is restricted and is directed into the adjacent film media with less pressure. Another gross waste of both pump and air energy. When the counterflow tower distribution system was designed, the logic was to use the velocity pressure produced by the pump to create an equal static pressure at each nozzle, resulting in a balanced water loading over the film media. The common problem with water distribution systems today is the static pressure at the nozzle tends to bleed off before the velocity pressure in the piping can fully charge the system. The result is uneven water loading across the system, often starving the lower end of the distribution system of water. This results in a waste of both fan and pump energy. In effect, the velocity pressure competes with the static pressure at the nozzle, resulting in the system not becoming fully charged. The net results of this is that no two nozzles receive equal water loading. In addition, aging and fouling of the pump system, improper orifices in the nozzle, fouling and or plugging of water spray nozzles, pump water being diverted to other processes, and under-designed pump capacity compounds the problem. Another side problem resulting from high-velocity airflow is enhanced drift loss, which wastes significant volumes of water. In most facilities, makeup water is as precious as fuel. Increased drift loss also corrodes and contaminates adjacent equipment. In areas where water lighting is light, evaporation accelerates, causing premature fouling of the film media. This increases service and maintenance costs,